All right, your book doesn't discuss this that much, but I think it's important to look at how do we know what the right mechanism is. And we've already discussed this a little bit. How do you know which is the right mechanism? The first thing to do is look for the intermediate. If your mechanism has a certain intermediate, and you find that that intermediate exists when you run the reaction, hey, your mechanism is very much supported by the data. Recall with the hydrogen iodide reaction that we just looked at with that fast equilibrium first step. They knew their mechanism was wrong, the one-step mechanism, because it could not account for free iodine atoms. Their new mechanism with the fast equilibrium first step and the slow second step could account for the iodine atoms, and therefore it's a better mechanism. It's more likely that that two-step mechanism is the mechanism for the overall reaction. Okay, there are other ways we can look for the intermediate. There are ways when you get to organic chemistry, nuclear magnetic resonance spectroscopy is really good, fluorescence spectroscopy. Try changing the conditions. One nice way to look for intermediates or figure out what the mechanism is isotopically labeled atoms. So here's a reaction. Methyl acetate, CH3, C double bond O, O, CH3, plus water goes to acetic acid, CH3, C double bond OOH, plus CH3OH. Well, we want to figure out how this reaction occurs. What is the mechanism of this reaction? And what we really are wondering is, hey, see that the CH3 C double bond O has this O here between the C double bond O and the CH3? See how in acetic acid that O is after the C double bond O, but now there's an H on it? The question is, this oxygen in acetic acid, did it come from the water, or did it come from this oxygen here in the methyl acetate? This oxygen right here in acetic acid, which oxygen is it? This oxygen here from methyl acetate, or this oxygen here from water? If we knew which oxygen this is, that would give us information about how the reaction occurs, what the mechanism would be. And so we could think of these two possibilities. Somehow this OCH3 breaks off from this carbon double bond oxygen and the OH from water gets on there. Or somehow the CH3 breaks off from this oxygen and one of these H's from water gets on there. Well, which is the way it works? The experiment is actually pretty straightforward as long as you have some radioactive water. Yeah, so you run the reaction using H2O, but every oxygen in the water is an O18. It's a radioactive isotope of oxygen. Recall, most oxygen that we come across is O16. It has 8 protons, 8 neutrons in the nucleus for a mass of 16. This is an isotope of oxygen with 8 protons in the nucleus and 10 neutrons in the nucleus. And it's radioactive. So if you hold up a Geiger counter to this H2O with the O18, it would be clicking due to the radioactivity. And so what they did was they ran our reaction up here, except they made sure all this water was our O18 water. And so then the question is, when you ran the reaction, you've got acetic acid and you've got methanol. Separate those two from each other, and which is radioactive? Is acetic acid radioactive, meaning it has the O18, or is the methanol radioactivity, meaning it has the O18? And what was found was that the acetic acid was radioactive. When you held up the Geiger counter to the beaker with acetic acid, it started clicking. The methanol did not, which means that the oxygen from this radioactive water is now on this acetic acid, which means this is more likely what happens. The OH comes from the OH that's in acetic acid. The OH in acetic acid here comes from the water because this H2O had the O18 in it, and the acetic acid at the end had the O18 in it. So that tells us more about the reaction. No, this is what occurs here. This OCH3 must split from that carbon somehow. Cool. And when looking at photosynthesis, it was done in a similar manner. Photosynthesis, a plant takes carbon dioxide plus water and forms glucose plus O2. And the question is, okay, these oxygens here in the glucose, do they come from the water or do they come from the CO2? Where do these oxygens come from? Well, they just fed the plant radioactive water. It did not kill the plant because it's not that radioactive. They just fed the O18 water, and they found out that all of the O18s ended up in the O2 here. The glucose, the oxygens in the glucose were not radioactive, which meant all the oxygens in the glucose came from the carbon dioxide. Cool. All right. The next topic, the last topic of this chapter, catalysis, using catalysts. Note, we've already seen catalysts in our reactions. It is something that you put in the reaction, it speeds up the reaction, and then it gets spit back out again. It does not get used up in the reaction. So if you added it to the reaction, at the end you still have that catalyst. It'll speed up the reaction, but will not get used up in the reaction. And catalysts work by lowering the activation energy. For example, if you had a reaction, here's potential energy versus reaction progress, and you had to, here's our big old activation energy here, you have to add this much energy. Recall, the more energy you have to add to get a reaction to go means the fewer collisions you're getting at any one time. Are fewer collisions with enough energy to overcome that barrier are occurring means the reaction is slow. The size of this hill tells us how slow the reactions are. And this is a large hill, so we know this reaction is very slow, but you can put in a catalyst, and that's indicated in red here. It might do something by lowering the activation energy by adding a second step in there. An intermediate could happen, but either way, it lowers the activation energy. This top red hill is much shorter than this one, which means more molecules have in their collisions enough energy to overcome this activation energy, and the reaction goes faster. So that's how catalysts work. They lower the activation energy. And there are two main types of catalysts, heterogeneous and homogeneous. We'll start with our heterogeneous catalysts. That's where our reactants and our catalysts are in different phases. Most likely what that means is most likely our reactants are either liquids or are dissolved in liquids. When that is the case, the most common phase of your catalyst is a solid. So your reactants are liquids or they are dissolved in liquids, so your reaction is in the liquid phase, and our catalyst is in the solid phase. But here's an example, the Auber synthesis of ammonia, where the reactants are in the gas phase. If you take N2 gas plus 3H2 gas, they will react to form 2NH3 gas. And this reaction, delta H, means the enthalpy of the reaction, the heat of the reaction, negative 92.6 kilojoules, which means it is exothermic. Ammonia is more stable than N2 and H2. So you would think this reaction would go nicely. However, it's extremely slow at room temperature. The activation energy is very high, mainly because N2 has a nitrogen-nitrogen triple bond, and we remember from Gen Chem 1 that triple bonds are very strong. And so breaking that nitrogen-nitrogen triple bond takes a lot of energy. That means it's got a very high activation energy, means this reaction is very, very slow. And the problem was, well, if it's very slow, we want to add energy, let's heat it up. Turns out when you heated it up, we're going to find out next chapter in equilibrium, since this is exothermic reaction, heating it up makes the ammonia want to just break down into N2 and H2 gas again. So that's not the best way to do it. But what Auber found was if you add solid iron that has small percentages of potassium oxides and aluminum oxides, reacted at only 500 degrees Celsius, you will get your ammonia. The iron with a small amount of the oxides on there is our heterogeneous catalyst. It is a solid, whereas our reactants are gases. And the way it works is like this. Our heterogeneous solid catalyst, we can look at this as like a surface, a piece of this iron with those oxides on there, and the N2 molecule gets attracted to this. The H2 molecules get attracted to it. And because the N2 is attracted to the surface, it breaks that triple bond, makes it much more like a double bond, which is more breakable, and then changes it to a single bond, and then the hydrogen bonds are broken, and these hydrogens can migrate across that surface to the nitrogens, and then ammonia will come off. So, heterogeneous catalyst usually provides a surface for the reaction to occur. Note, after this ammonia comes off, you've got that catalyst surface again for more nitrogen and hydrogen to come in and do the reaction. But the reaction, the interaction of the nitrogens and hydrogens on the surface of this catalyst lowered the activation energy. It weakened that nitrogen-nitrogen triple bond, lowering the activation energy, allowing this reaction to occur. Another heterogeneous catalyst reaction is the Oswald process to produce nitric acid. The catalyst part comes a little early in the mechanism. If you take ammonia and react it with O2 gas at 800 degrees Celsius with a platinum rhodium catalyst, solid pieces of platinum and rhodium mixed together in there, you'll get nitric oxide, NO gas, plus 6 H2O, and at 800 degrees, H2O is a gas. Note it is heterogeneous because the platinum and rhodium are solids, everything else is a gas. Turns out that's the slow step. The catalyst lowered the activation energy to make the NO gas, and the NO gas through this process here that you don't have to worry about eventually turns into nitric acid. All right. More examples. Turns out catalysts are pretty darn important to us. All right, catalytic converters in cars. If you are driving a car, it has a catalytic converter in there, and they tend to run $1,000 to $2,000. Which is why if you drive certain cars, especially like a pickup truck that's raised, you have to watch it sometimes when you're parking it outside overnight, because thieves will come in and cut out that catalytic converter, because they can get some serious money for a fairly new catalytic converter that they cut out of a truck. All right, so let's not do that though. Let's use our knowledge for good and not for evil. But let's look at catalytic converters. There's a problem that we have with our cars in that when your car burns gasoline, it also needs oxygen, and it gets the oxygen from the air. So your car sucks in air through the air filter to burn, but that oxygen is a mixture of nitrogen and oxygen gas. And at engine temperatures, this reaction occurs. A lot of that oxygen gas goes to burning the gasoline, but some of it reacts with the nitrogen to form NO gas. And NO gas is going to react with O2 to form NO2 gas, which is this brown nasty stuff, and we got all this pollution, and it's bad for the environment. But attached to your tailpipe, as the exhaust gases are leaving the car, and they're very, very hot, they are going to run into your catalytic converter, along with carbon monoxide that got released from the engine and some unburned hydrocarbons. And we don't want those going in the air. They go through the catalytic converter, which is just beads of platinum, palladium, and rhodium, and usually transition metal oxides. And what these metals do is they catalyze the reaction of carbon monoxide and our hydrocarbons get reacted and form CO2 and H2O. And it also will reduce nitric oxide and NO2 back to N2 and O2. So these catalysts mean what's coming out of the tailpipe is basically air, N2 and O2, but with a lot of CO2 and H2O. Note there's a lot of CO2 in there and H2O, so it's not air that's really coming out of the tailpipe, but it's gases mainly CO2, 8 water vapor, with some N2 and O2. But what is not coming out of the tailpipe, hopefully, is unburned hydrocarbons, carbon monoxide, and these NO and NO2 gases, which are much worse for the environment and for your health. All right, so those are all heterogeneous catalysts because everything is in the gas phase here, and your catalyst, this piece of platinum palladium, they are solid. The other type of catalyst is a homogeneous catalyst. This is when the reactants and the catalyst are in the same phase. All right, they get involved in the reaction. Here's a set of reactions. If you want to produce sulfuric acid, and sometimes we don't, but it'll happen anyway, solid sulfur plus O2 gas goes to SO2 gas. When SO2 gas finds oxygen gas, it forms 2SO3, SO3 gas. Water plus SO3 gas reacts to form H2SO4, sulfuric acid. The problem with this, part of the problem with this, is that when you burn coal or when you burn oil, any of these power plants that burn coal or oil, they release this SO2 gas up the chimney. And this SO2 gas, when it's up the chimney, then can find oxygen gas and make SO3. And when that SO3 finds rain, water in the form of rain, sulfuric acid rains down out of the skies. And this was a big, big problem in the 1970s and early 1980s. All right. If you've ever heard from medieval literature of the Black Forests in Europe, the Black Forests in Europe aren't Black Forests anymore. They're actually easier to walk through because acid rain has killed off a lot of the plant life. However, the problem with this, which says, most people say, oh, it's not too much problem because this second step is very, very slow. SO2 reacting with O2 to form the SO3 is a very, very slow reaction, so we don't have to worry about it. The problem is the second reaction can be catalyzed with NO2. If you have two SO2 gases, instead of reacting with O2 like up here, they can react with 2 NO gas to form SO3 plus nitric oxide gas. And then nitric oxide gas can react with O2 to form 2 NO2 gases, molecules again. If you look at this, the overall reaction is SO2 plus O2 goes to 2SO3. And this nitrogen dioxide was here, and then it gets spit out again here, so it's the catalyst of this reaction. And that lowers the activation energy, makes this reaction happen much faster. And so part of the problem with acid rain, it's a two-pronged problem. One is that these smokestacks were releasing all this SO2 gas, and the other is cars and everything were releasing a lot of NO2 gas. So the cars, and truthfully burning the air, if they're using this air for this form of oxygen, or for the oxygen in this reaction here, then they were forming NO2 gas also. So even though this step is very slow, it is catalyzed by this homogeneous catalyst because, note, the NO2 is also in the gas phase. And when you have a homogeneous catalyst, it's usually a two-step reaction where the catalyst reacts with one of our molecules, and then another reaction happens to regenerate that catalyst again. All right. And another type of catalyst that you deal with all the time in your body is enzyme catalysis. Enzymes are proteins in your bodies that catalyze reactions, to make reactions go the way they want them to in your body. These catalysts can increase the rate of a biochemical reaction by 1 million to, oh my goodness, I don't even know what 10 to the 12th is. That's 1 million, 10 to the 6 is 1 million, 1 billion, trillion, it's more than a trillion times faster due to these catalysts. The interesting thing about these catalysts are they're very highly specific. They are only going to react with certain molecules. An example of this in your body, most of you have a molecule called alcohol dehydrogenase. It is a molecule that takes ethanol that you might find in alcoholic beverages. I do not recommend drinking alcoholic beverages while you're studying chemistry. The alcoholic beverages contain this ethanol, and when you drink that, the alcohol dehydrogenase changes it into this beast here called acetaldehyde. Now, acetaldehyde doesn't make you feel drunk. It's this ethanol that makes you feel tipsy and not feeling very well. But your body has some trouble getting rid of this. Alcohol dehydrogenase found in your liver slowly will get rid of this ethanol and make this acetaldehyde. Now, acetaldehyde is more poisonous than our alcohol is. However, your body can easily break this down into other things. Okay. There are some people that have very, very little alcohol dehydrogenase, and that's not good, because if they have, just half of a drink, if they don't have to drink hardly any alcohol, and they are going to stay tipsy for a long period of time, because they have to wait for their body to get rid of this alcohol without the alcohol dehydrogenase, which means it's going to be a very slow process. Some people, I have a brother-in-law who actually his body has a whole lot of alcohol dehydrogenase, and so he has a problem that whenever he drinks alcohol, it never affects him whatsoever, because as soon as he drinks it, he's got so much alcohol dehydrogenase in him that it almost all converts to the more poisonous acetaldehyde, and he gets super sick because he makes so much acetaldehyde, his body makes so much acetaldehyde so quickly that really makes him sick, because now he has to wait for the other enzymes to get rid of that extra acetaldehyde. But he cannot get drunk at all, because as soon as he drinks that alcohol, his body gets rid of the alcohol and makes the more toxic substance, which then hangs around for a little bit longer. All right, so catalyst is very important. This is just one example of a catalyst, and I realize if you're under the age of 21, you don't even know what we're talking about, because you've never heard of alcohol. All right, enzymes will do this, and the enzyme is the protein. The substrate is the other reactant that it goes with. So alcohol dehydrogenase is the enzyme. The alcohol, this ethanol here, is the substrate. Note this is homogeneous catalyst because they're both in solution. All right. And so the way it works, your enzyme tends to be a large protein molecule with one or more active sites where the substrate can interact. Kind of like a lock and a key, and experimentally it's more complex than this, but we can kind of break it down. The enzyme plus the substrate is in a fast equilibrium first step with this enzyme substrate complex. Once this enzyme substrate complex forms, in a slower reaction, it can break that substrate down into the products and release the enzyme again. So enzyme plus alcohol forms this alcohol dehydrogenase plus our alcohol forms this complex where the alcohol is bonded to the alcohol dehydrogenase, and then that breaks up into our acetaldehyde and releases that enzyme again. It's a catalyst. It can go back in and go through this cycle. And note, here in your body is an example of those fast equilibrium first step, slow second step reactions. So one might be asked to figure out the rate law for the slow step, the rate law for the fast step, and the experimentally determined rate law, and mathematically get those two to equal each other. But as we have said before, without a catalyst, if here's a substrate and here's a product, without a catalyst you have very high activation energy. You put the catalyst in there, the enzyme reacts with the substrate to make the enzyme substrate intermediate, which then breaks up to the products, and you have a lower activation energy, which means the reaction goes faster. Note, however, there's only a certain speed the reaction can go, because in general you don't have a whole lot of enzyme. That's why it takes about an hour to metabolize 1 ounce or 1 drink of alcohol, 1 beer, 1 glass of wine takes about an hour to metabolize it, because most people do not have a ton of these enzymes. And so the rate of product formation will go up as you get more and more substrate. The rate of product formation goes up and up and up until eventually you run out of enzyme, and then it levels off. All right, that is it for the kinetics chapter. We will be coming back at the end of the equilibrium chapter to look at kinetics and equilibrium and lots of more mathematical fun.